Section 2.1, a preview of calculus. The tangent problem and differential calculus. So in the table below, we'll find the average rate of change of two functions in 3 intervals. And if you can remember what is an average rate of change, if you can remember back to algebra or even pre-calculus, it's really a slope. We take the y functions, remember the y2 minus y1 over x2 minus x1, and we find the slope of this particular function that we're looking at. And you can see we're looking at 3 different intervals. We're looking from where x is 2 and x is 1. Then we're looking for x is 3 to 2, and then 4 to 3. So you can look at the different intervals that we're looking for. So from 1 to 2, 2 to 3, and 3 to 4. And we can see they're all the same. So what does that tell us? That tells us we have a line because the slope doesn't change. Let's look at this other function that we have, and let's look at the intervals 1 to 2. We get an average rate of change of 3. We look from 2 to 3, we get an average rate change of 5, and then we look 3 to 4, and you can see we have a average rate of change of 7. And if we graph this function, you see we have a parabola here. So what does that tell us? That tells the average rate of change does not change for a line. In fact, it's the same. It's as an instantaneous rate of change, and that is the slope. So no matter which intervals we look at, the average rate of change is not different. It's the same. However, when we look at our other function, the average rate of change does change. It's not the same in the different intervals. So if we're asked to find an instantaneous rate of change at x equals 2, then we can say that since the rate does not change, the rate at x equals 2 is 2. But for the other function, the same question is more subtle. Is the rate at x equals 2, 3, or 5, or none? This is the question that was finally answered by calculus. What is this rate of change that we're looking at? What if we want to answer the question without using calculus? Well, we can approximate the answer. But how do we do that? Well, we can say the rate is approximately 3 or 5, but can we do better than that? Well, yes, of course we can, and we will. We use x values very close to 2. For example, 2.1, 2.01, 2.001, or 2.0001. And you can see these are all very close to 2. And actually it gets closer and closer to the value of 2. And the closer it is, the better the approximation we're looking at. So we use the secant. And what is the secant line or a secant to a function? Well, you can see it intersects at 2 different points the curve. So it's a secant line. And you can see, again, it intersects at 2 spots of the curve, or 2 parts of the curve. So definition is the secant to the function f of x through the points a, and then f of a, and x, and f of x. So you can see those points here. Sorry, here we have f of a, and here's f of x, is the line passing through these points. So we're going to look for the slope of that secant line. And sometimes you may see it looking like this, x plus h, where h is going to be a number that's really close to x. That's where if x is 2, for example, then we might have 2.0001, which would be very close to x, or 2.00x. So it might be 2 plus 0.001, 2 plus 0.01, and so on, where h is the change that's happening. What's the difference between those values? And you might see it as well looking with f of a that we'll plug in. Okay. So, if we clicked on this image here, then and moved the blue points to create the secant line from A to f of A to x, or sorry, from A to f of A to x to f of x, and a tangent line at that point, A f of A here. Note that the closer the 2 points are, the closer the equations of the secant lines are. So let's take a look at that. Okay, so we have our function here, and so for example, if we move, here's my A and f of A, and you can see my secant line as I get closer to x. So you can kind of look at the values over here change. Okay, so as I move closer and closer to x, you can see that secant line, and as the further away I get, the worse it is, but as I get closer and closer to x, it gets really close to those values as well. As we get closer and closer and closer, and you can see how close these values get to this. So the tangent line is where it just touches. So when I get exactly there, that would be the tangent line. It just touches at that point. But the secant line is an interval. Okay, it may be very small between the two, but it is an interval depending how far away we are. The closer it gets, the more accurate our slope or our rate of change will be. So that's kind of neat to be able to visually see. The closer we get, the better. And again, a tangent line touches at just the one point of the curve, where a secant line would be 2 points connected by a line. That's our secant line, the dotted line, as you can see. So, and the red line is the tangent line, and you can see as it gets closer and closer, it can actually be that same line there. But anyway, kind of neat to look at that. You can see as the values get closer, we get a better approximation. So what would be a reasonable definition of instantaneous velocity? So let's say s of t to be a position of an object moving along a coordinate axis at time t. So s of t, t is time, that's our input. The average velocity of that object over a time interval, a to t, where a is less than t, or as you can see at interval, t would be less than a if we're looking at an interval, if t is less than a. So again, interval notation here. And we want to find the average velocity. We would look at s of t minus s of a over t minus a. So there's that average rate of change again. So as t is chosen closer to a, the average velocity becomes closer to an instantaneous velocity. So that instantaneous velocity would be that tangent line, the velocity at that particular point. The average velocity of a position function over a time interval is essentially the same as finding the slope of a secant line to a function. So average velocity, we're trying to be as close as we can to that point to see what the velocity is. Instantaneous velocity would be at that point, and we'll look at that here in a little bit. So average rate of change, find the slope of the secant line on an interval. All right, let's go back to that instantaneous velocity. The process of letting x or t approach a in an expression is called taking a limit. Now this is the limit concept. Thus we may define the instantaneous velocity as follows. For a position function s of t, the instantaneous velocity at time t equals a is the value that the average velocities approach on intervals of the form a to t and t to a as the value of t becomes closer to a, provided such a value exists. All right, so we have s of t minus s of a, t minus a, where v of a, velocity, when t approaches a. So as t gets closer to a, that's what we're talking about, as t gets really close to a. Or you may see it written as such, where we have S, A plus H. So again, it's this value's getting close. It's just a little bit above or a little bit beyond A minus S of A divided by that H value as H approaches 0. Because think about that. As H goes to 0, we get to A. So this would be the same. All right. So as an object moves along a coordinate axis so that its position at time t is given by S of t equals t cubed. Estimate its instantaneous velocity at time t equals 2 by computing its average velocity over the time interval 2.001. And this is just showing you how you can use your calculator to do this. If you have the TI-83 or 84, you can actually graph the calculator and plug in your y1s as x is approaching 0 here. So it's, again, this is showing you how to put it in your calculator. And then when you go to your table, okay, and think about what happens when h equals 0. It's going to be undefined at that value because we're dividing by 0. So you won't actually get there. So there's an error there, and that would be it. But think about as we come from the left side, right, or the right side, excuse me. This would be coming from the positive side, coming from the negative side of 0. Right, we're getting really close to 0, but you can see what are our y values getting close to. And so that's giving us our limit as h approaches 0. So as it gets closer and closer to 0, from the left, closer to 0 from the left, closer to 0 from the right, we get to 12. And that would be our limit for this particular